topic I want to talk about is the ideal gas law. And the ideal gas law basically relates all the variables that I just talked about, like the pressure, volume, temperature, and the amount, and it relates it into one big old equation. So the ideal gas law is what I'm talking about now. Ideal gas law. So the main difference in the ideal gas law and the simple gas laws, remember for the simple gas laws, I'm usually talking about two different variables like the pressure and the volume, or the volume and the temperature, or the pressure and the temperature. In the ideal gas law, I can relate the pressure, volume, I'll say it relates. Pressure, volume, temperature, and amount. So it relates all of the variables in one big equation. When I talk about,
I'm sorry, N stands for amount?
Yep, the amount in moles. So remember?
Okay.
Yeah, N is just equal to moles. So how many particles you have. So when we talk about ideal gas laws, and then we talk about an ideal gas, all an ideal gas is when you have a gas at low pressures and high temperatures. We say these are ideal gases. When we use the ideal gas law, I'm just going to tell you what it is. I'm not going to derive it for you. I'm just going to get straight to it. The ideal gas law says that the pressure times the volume is equal to the amount of moles times a gas constant times the temperature in Kelvin. All right, so when we talk about these things, remember P stands for pressure. I'm going to say pressure. Our pressure needs to be in atmosphere. V stands for volume. Our volume needs to be in liters. N stands for the amount, and I'm just going to say it's basically moles. R is a constant. This is a constant. It's called the gas constant. And the gas constant that we're going to use for this equation is 0.0821. And the unit for it is liters times atmosphere divided by moles times K. This is one big old unit. Basically, it's basically using all of these units, combining it into one to get this number. And then finally, T stands for temperature. And the temperature needs to be in Kelvin. Now, the main difference, we know to use the ideal gas law is when you have 3 of 4 of these variables. You're always going to have R. It's always going to be given to you. So the other variables, the P, V, N, and T, that's 4 variables that we care about. If I know 3 of them, I can solve for the 4th one. If I know P, V, and N, I can solve for T. If I know N and T and V, I can solve for P. So I know to use the ideal gas law because it's going to give me 3 of these variables. And those 3 variables, I need to find the 4th one. It's not gonna say the pressure started off with this and then it ended as this. What's the new volume? It's not gonna ask you those things. It's simply gonna say, I know the pressure, I know the volume, I know the temperature, how many moles is there? Do we get the difference between the ideal gas law and the simple gas laws? Because that comes up a lot too, guys. It's just, I'm not asking an initial and final of any of these variables. I'm saying I know 3 of them. I want to figure out what the 4th one is. So let me give you an example of when we'd use the ideal gas law. The example says, let's calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmosphere and a temperature of 315 K. All right, so in this equation, this question, it's asking me to calculate the volume. It's giving me the amount of moles. It's giving me the pressure, and it's giving me the temperature. These are the 3 variables that I know. I'm looking for the 4th one, which is the volume. So in this case, I can use the ideal gas law, PV equals nRT. I'm looking for volume in this case. So I'm going to plug in everything I know. Remember, R is always going to be given to you. It's this number right here. It's a constant. You're always going to know R. It's a gas constant. There are lots of different gas constants that have different units, but we're going to use the one that has units of liters, atmosphere, mole, K, because that's what we're working with, and we need our units to cancel out. So if I change the units on this gas constant, it's going to change the number on the gas constant. So if you see other gas constants out there, that's fine. They just most likely have different units. All right. When I plug everything in this case, my pressure, what's my pressure, guys? Let's just go and make sure we can recognize each variable. Which one's my pressure?
1.37.
1.37. Atmosphere. That's my pressure. So I'm saying pressure times volume. What's my volume?
We don't know.
We don't know. That's what we're looking for. So I'm going to put B. What's my N?
0.845.
0.845 moles. That's my N. And then my R, remember, it's always going to be this number, which is 0.0821 liters times atmosphere, mole times K. And then finally, what's my temperature?
315.
315. In this case, it's already given to me in Kelvin. I don't have to worry about changing it to Kelvin. So I just need to solve for V. And to solve for V, remember I say I like to get one number on this side, but in this case, I'm gonna just go ahead and say all V is equal to is this whole sentence multiplied by each other divided by 1.37. Do we see that? Do we see that we're multiplying all this together, then dividing it by 1.37 to get V? So I'm saying V is 0.845 times 0.0821 times 315 divided by 1.37. This is essentially what we're putting in our calculator.
So is liter is for where's that? R liters times pressure over moles times temperature. Is that just the unit?
Yep, so we want that to be the unit because if we look at it, we have moles right here at the top, and then we have moles at the bottom. We have K at the top, we have K at the bottom. And then when we divide each side by atmosphere, we're gonna have atmosphere at the top and atmosphere at the bottom. And so we're gonna just be left with units of liters. And that's what we're looking for. Now, remember I'm saying if we have different gas constants out there, if you Google gas constant, it'll give you a list of several different numbers, but these numbers, these other numbers have different units. So we want the units with liters, atmosphere, moles, and K, and this is the number for it. And that number comes from basically STP, and I'll explain that in a second.
You're saying that the R does change, right? It's not always 0.
In this class, it's not gonna change.
Okay,
So I'm saying, in general, if you Google gas constant, you might see a list of several different numbers. One we're using in this class is this number because we want these units. So basically it's saying, what if I change my atmosphere to millimeters of mercury? If I change it to millimeters of mercury, it's gonna change this number. Or what if I change my liters to milliliters? If I change my liters to milliliters, you get what I'm saying?
yeah, that's because we do liters and the pressure and the moles. Okay,
Yeah.
I see.
So we put this all in our calculator, and what'd you guys get once you put it in your calculator?
16.0 liters.
All right, so we see that we need 3 sig figs. Once we do all this with 3 sig figs, we're gonna get 16.0 liters. All right, so I just want to point out the main difference in the ideal gas law and the simple gas laws. The main difference is the simple gas laws only relate 2 or 3 variables at a time. So meaning, like I said, if the pressure goes up, the volume's gonna go down. So that's saying that I'm relating the pressure and the volume. Or I can say if the temperature goes up, the volume's gonna go up, and that's relating the temperature and the volume only. When I relate all the variables, all the different measurements of gases, like if I relate the pressure, the volume, the temperature, and the amount, I can use the ideal gas law. So in this question here, you see there's no like the initial temperature was this, and then the final temperature is this. What's the new pressure? It's not asking you questions like that. It's just simply saying, these are what I know. What's the missing variable? In this case, my missing variable is the volume. So do you guys see what I mean? The difference in these two types of laws. Okay, great. So if I keep going, I'm out of paper. If I keep going, remember we talked about STP. We talked about it a few chapters ago, and I related STP to you guys when we were talking about the mole concept. So STP, just to refresh your memory, STP stands for standard temperature and pressure. We'll get some more, I don't have any. Give me some too. Standard temperature and pressure. So STP says that 1 atmosphere is the standard pressure. The standard temperature is 273.15 K, or 0 degrees Celsius. And we can say at STP, remember we can use the molar volume. And the molar volume said that 1 mole of any gas equals 22.4 liters. You guys remember this? When we were talking about the
Yeah.
mole concept, we had Mole Island, and
Yeah.
we said anytime you want to convert back and forth to moles, as long as your gases are at STP, we can use the molar volume. Let me just make sure to say this is the molar volume. So if we plug all these numbers in, if we plug in 1 mole, 22.4 liters, 1 atmosphere, and 273.15 K into the ideal gas law, and basically solve for R, we end up getting the gas constant, which is that 0.0821 liters atmosphere moles over K, and vice versa. So basically, we can solve for the molar volume this way, or we can solve for the ideal gas constant this way as well. So basically, if I plugged in the ideal gas constant and solve for volume, I'm going to get 22.4 liters as my molar volume. But what I'm reminding you guys this of is because we can use stoichiometry in gases as well. So remember, ultimately, we can go from use the ideal gas law to solve for the amount of moles, or we could use the molar volume to solve for the amount of moles. So let's say, for instance, I know the pressure, volume, and temperature. If I know the pressure, volume, and temperature, that means I can solve for the amount of moles, because that means I know P, V, and T. So if I know P, V, and T, I can get N. So if I plug P, V, and T into the ideal gas law, I can solve for N, and that will give me the amount of moles. Once I get the amount of moles of one substance, how do I write this out? Gives me moles. And I can say moles of A. I can say this is moles of A. And remember, once I get to moles of A, as long as I have a balanced chemical equation, I can solve for moles of B just by using the mole to mole ratio. So remember, moles of A go at the bottom, moles of B go at the top. And then I can solve for whatever it is I'm looking for. So what I'm looking for sometimes might be just grams. So I can say moles of B, and on top, I'm gonna put the grams of B. And that is from, so this is from the balanced chemical equation. And then this is the molar mass of B. So essentially, I'm saying my whole point is to always solve for moles, no matter how I have to solve for moles. You know, I can solve for moles. If I have particles, I use Avogadro's number to solve for moles. If I have liters, I can either use the molar volume to solve for moles, or if I know the pressure, volume, and temperature, I can use the ideal gas law to solve for moles. So let me write that here. Use ideal gas law to solve for moles of A. So if I know the pressure, volume, and temperature, I can use the ideal gas law to solve for moles. And once I know the moles of one substance, I can convert it to the moles of another substance just by using the balanced chemical equation. So let's do an example so I show you guys what I mean. Let me find my example. All right. Here's my example. My example says, in the following reaction, 4.58 liters of oxygen gas were formed at 745 millimeters of mercury and 308 Kelvin. How many grams silver oxide the reaction says? All right, so if we talk through this example. So we have this reaction. It's a decomposition reaction. We have the silver oxide. It decomposes into just silver and oxygen gas. And it says that at 745 millimeters of mercury and 308 Kelvin, I have 4.58 liters of oxygen gas. So what I'm saying here for my oxygen gas is I have a pressure, which is 745 millimeters of mercury. I have a volume, which is 4.58 liters. And I have a temperature, which is 308 Kelvin. So if I have 3 out of the 4 variables, especially pressure, volume, and temperature, I can use the ideal gas law to solve for the moles of A, and in this case, I can use the ideal gas law to solve for moles of oxygen gas. So that's what I'm gonna do first. I'm gonna say, use ideal gas law to solve for moles of oxygen gas. So you guys help me set this up. Right now, I'm going to use the ideal gas law to solve for oxygen gas, which simply says I'm going to solve for N in the ideal gas law. And if I solve for N, I'm saying N equals PV over RT. So you guys help me set that first part up, and then I'll continue to go. All right, so were we able to solve for the amount of moles?
Yep.
Okay, what'd you guys
Yeah.
get? Amount of moles?
135.
135.
Okay, so we plugged everything in. We say the amount of moles equals 135 moles. So give it to me with the decimal so I don't round too fast. 135 what?
134.9. That's what I end up with.
134.9?
Yeah.
Okay, so 134.9 moles, that's fine. So that's our first step. Now that we know the amount of moles, and this is moles of oxygen gas, I can now just go through my stoichiometry steps to figure out how much silver oxide, because ultimately, remember, I'm trying to figure out the grams of silver oxide, so I can use my balanced equation to figure out the moles of B and then convert moles of B to grams of B by using the molar mass of B. So if I set this up, I'm gonna say 134.9, and this is moles of oxygen gas. I want to convert my moles of oxygen gas to moles of silver oxide, because anytime I go from one substance to another, I have to use this balanced equation that says the mole to mole ratio is what, guys?
2 moles of silver oxide for 1 mole of oxygen.
Great, 2 moles of silver oxide for 1 mole of oxygen gas. All right, and I got that from the balanced equation. The ratio is 2 to 1. And then finally, I can say, okay, I'm out of moles of oxygen gas. For every 1 mole of silver oxide, I need the molar mass of silver oxide. Does anyone have the molar mass of silver oxide?
231.74 grams.
271.74 grams of silver oxide. And now I've converted my moles of silver oxide to grams of silver oxide. And that, once I put this all in my calculator, and let's say, what do I start off with? It looks like 3 sig figs is the least amount of sig figs. So my answer should be expressed to 3 sig figs. What's that? Does anyone have an answer?
Yeah, I got, well, I think I gave you the wrong grammage for
Okay.
silver oxide. Let me see what I had. It was 231.74.
Okay. 231. Let's
Uh,
make 31.
Otherwise, I had 6.252 times 10 to the 4 times 10 to the 4.
Okay,
Right.
so you're basically saying you have 62,500.
Yeah, so is it 3 sig figs were?
Yep, we're gonna do 3 sig figs. I only have 134.9 because I didn't want to round into the end right here.
Oh, got it.
Ultimately, these were all 3 sig figs, so the least amount of sig figs is 3 sig figs. Remember, this is all multiplication and division.
Got
So least amount of sig figs, 3 sig figs. We got this with grams. Another way, and this is grams of silver oxide. Another way I can say this is 6.25 times 10 to the 4 grams of silver oxide.
I'm kind of confused as how we got 134.9. I mean, you just do 745 and multiply 4.58 divided by 308.
Yep, and the R. Don't forget about the R, which is the 0.0.
Okay.
Yeah, so I literally just plugged it in here. P times V, and you just gotta remember that R is 0.0821 times 308. And once you get the amount of moles, so, you use the ideal gas law to solve for moles, and then once you get your moles, you can convert your moles to the other substance's moles with the mole ratio, and then multiply by the molar mass to get the grams.
Okay.
All right, now sometimes the problem might be given the opposite way, to where they start and give you the grams first. And if they give you the grams first and ask you to solve for P, V, or T, you just do it backwards. So let's say I start off with grams, I then need to convert to moles, use the mole ratio to convert to moles of my other substance, and then plug in to the ideal gas law and solve for the missing variable. So it could be asked either way. I I do want to show you one more example and then I'll wrap up for today. I'll tell you what the extra credit is. My last example. So remember, I said we can use PV and T to solve for the amount of moles, or we can just always go back to the molar volume and use the molar volume to solve for the amount of moles when we talk about gases, if and only if we're at STP. So this has to be at STP, and if we're at STP, we can figure out, we can just use the molar volume to figure things out, and let me show you what I mean by that. He doesn't get one. Okay. All right, so let's do another example, and I want to show the main differences. This next example is going to say I'm at STP. Huh? Okay. All right, so my next example just says how many grams of water form when 1.24 liters of hydrogen gas at STP completely react with oxygen gas. All right, and let me give you the reaction. The reaction in this case is if I have hydrogen gas, let me write it correctly. If I have hydrogen gas plus oxygen gas, it reacts to form water vapors, like this. This is my equation. My main point is that we are at STP. If we are at STP, we can assume that the volume of any gas, 1 mole of any gas, is equal to 22.4 liters. 1 mole equals 22.4 liters. So if I have these gases, I can still use stoichiometry that says, okay, I know the volume. The first step is to get to moles. To get to moles, I'm going to use the molar volume in this case. Once I get to moles, I can get to moles of B by just using the mole to mole ratio, and then I can convert my moles of B to grams of B. So let's just talk through this together. I'm simply saying if I start off with 1.24 liters, my first step, instead of starting off with grams, I'm starting off with liters. I'm saying 1 mole of hydrogen gas, because I have 1.24 liters of hydrogen gas, is equal to 22.4 liters of hydrogen gas. My next step simply says, let's just use the mole to mole ratio. What's the mole to mole ratio, guys, from hydrogen gas to oxygen gas?
1.
1 to what?
101.
For hydrogen gas to
I
oxygen gas?
mean, sorry.
2
Hydrogen, 1 oxygen.
2 to 1.
Look,
Oh,
yeah, there's 2
2 to 2.
hydrogens, there's one oxygen. So I'm gonna say 2 moles of H2 for 1 mole of oxygen gas. And then the last step says, oh, sorry guys, that's why you were saying 1 to 1 or 2 to 2. It's asking me about water, and I'm going to the wrong one. So if I'm looking at water,
Oh, okay. So I was right. Thank.
yeah, you are, sorry.
Okay.
It's asking me about water. It says how many grams of water. So it's 2 to 2, or you can say 1 to 1. We're looking at this one, 2 to 2. And then it says, and then my last step just says 1 mole of water. And I know the molar mass of water is 18.02 grams. All right, so let's put this in our calculator. Let's solve it to 3 sig figs. And let me know what you guys get. All right, we got 0.998, and I can second that because that's what I got. So 0.998, and this is going to be grams of water. All right, any questions on how I got this, guys? This is the easier one. If it's at STP, you know, we know how to go from liters to moles using the molar volume. When you do not have a gas at STP. So for instance, this last reaction, these are not STP terms. You know, standard temperature and pressure says 1 atmosphere, 273 K. This is not STP. So since it's not at STP, we have to go through the ideal gas law to solve for the amount of moles. If we use, you know, the 1 atmosphere and the temperature 273, we plugged all that in the volume of 22.4 liters. If we plugged PV and T into the ideal gas law, it would have given us the same answer. So if you went about it to solve it this way as well, you would have gotten the same answer. This is just, it saves time because you don't have to do the extra steps. Does that make sense to you guys? Like if you
Yes.
set it up like I did the previous one, you just have to know what STP stands for. You would have gotten the same answer. But this is kind of a shortcut, quicker way. So either way, we got to know how to use gas stoichiometry. I call this gas stoichiometry. The only difference is we're just going to use the ideal gas law to solve for the amount of moles versus normally we'd start off with grams. And if we start off with grams, we could just use the molar mass. This time we're going to start off knowing a pressure, volume, and temperature, and we use the ideal gas law to solve for the amount of moles.